Okay, so good evening, everyone. We let us start. So today we'll be ending with the GATE syllabus that you have, or the undergraduate level machine learning related and mathematics related question. All the topics that we have done: linear algebra, statistics, and machine learning. All the topics related to machine learning and its backgrounds we will be ending today, and you can look closely to the GATE syllabus that we have, and we have covered all of the three, or rather the four subjects in detail. That is machine learning in detail, linear algebra, probability and statistics, and also calculus. I have told you about Lagrangian and optimization problems. So all the four things we have covered in details, with more details than one would need. And other than that, we have also, what you can do is, other than that, you have only a few subjects remaining: algorithms and DBMS and networks. And then that would complete your syllabus. There are more of your CS core fundamental things which you need to do. But regardless, other than that, it's okay. So our goal to understand machine learning and all the, say, 60 for the, say, 70% of the syllabus of the GATE, or 70% of the weightage in GATE is completed. And also we have also delved into each of these algorithm with great details, trying to code them. And in the assignments also, you'll be coding some for practical purposes, so that you can also have a hands-on experience, so that if you're even in the interested in industry, this is the max that you'll be doing in the industries as well after an undergraduate degree. So you would be knowing everything that you require to join the research labs in any industry, like Samsung Research and so on. Okay, so what I'll try today is, I'll try to talk about a feature called dimensionality reduction. So why? So this has a very nice motivation that you can think about. So when you have large number of features, say if you have a very, say, 1,000 features, and only this is, I'm just contriving in one example and one training example, or say even 10 features and one, or 5 features and one training example. And if you want to model this data, y equal to, as y equal to w1 x1 w2 x2 w3 w5 x5 plus w0, right? Or even if I remove w0 for the time being, you can easily do it, right? So if you're given one training example x comma y, right, x1 x2 dot x5 are the features that you're given, and you're given the target level for this training example. Okay, right? So for example, you're given 2, 3, 6, and your y is, say, 7. Right? So I can, in this case, do you agree that I can set all w2 to w5 systematically to 0 and make w1 equal to 7/2, and that would solve my, that would train the model, that will overfit the data? Yes or no?
Yes.
So, but then when you're given a new example, your decision boundary has become w equal to 7/2x. This is nothing but this line. But in reality, your data must be, their data may be like this. Let me draw this data a little differently, maybe like this. And this one point that you had determined everything for you. So for you may have, this could have been the proper, I'm drawing with, say, summary of the features over here. Just try to understand. Or let us draw with only x1. So this is, say, the graph with only x1. Just think what bad it will be with 5 variables. So I'll say all the other variables in the actual distribution of the data was something like this. It was negatively correlated. But you have learned that y equal to 7/2 from this data point. So totally you will do very bad on unseen data, yes or no? You will
Yes.
do. The similar thing will happen when you have, say, 10,000 features or 100,000 features, 1 lakh features. and only 100 or 1000 examples. So what will happen? So you will have summation of W1 Wi x I j equal to 1 to 1 lakh equal to y1, and this you will do for say 1000 examples, right? Even simple linear regression is overfitting. Think of what will happen to complex models like MLPs that we have learned, right? Or like SVMs that we have learned, which can deal with non-linearity in the data and all. They can all be very, very easily, they'll overfit. So here also, you see what will happen. Systematically, you can learn delta Dirac functions, right? So say W1 you can map to Y1, W2 you can map to Y2, dot 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 W1000 or 1 lakh you can map to Y, or 1 lakh you can map to W1 lakh. Yes or no? That is for X1 Xi to Yi pairing, you can always learn the Wi-th weight as Yi by Xi. Yes or no? If number of examples less than training data, feature size, feature dimension. Is the motivation clear? Is this clear that how I did this? And all Wj not equal is equal to 0, J not equal to I, right? Agreed? So this way, oh, you are thinking, yeah.
Like means one thing for the ith case, we are calculating Wi by
No,
this
yeah,
logic you explained.
correct. You are right. I just so Wi you can calculate, but you cannot put everything to 0. For the time being, think that we are going to contrive it, like it's a neural network or something like that. So
So like we using that Gauss elimination of matrix, we
yes,
can do W1 we find, then put in W2 to get W2.
exactly. So the idea is the if you just I'll just remove this. This is not right because I'm using a linear regression model. So you have number of equations is it's a how many dimensional data? 10,000, 1,000, 100,000 into 1,000, only 1,000, or rather 1,000 cross 10 to the power 3 cross 10 to the power 6, 5, right? So what I'll do is I'll select only a 10 to the power 3 by 10 to the power 3 matrix, right? And then solve for the 10 to the power 3 examples, right? Yes or no? Like you're telling. And rest of it will be 0. So you will have a null space of this matrix plus a particular solution of the matrix. Right? We have seen this. Yes or no?
Yes, yes.
So, concretely speaking, so if you have 10 equations, you will solve for the 10 equations. Others you can just have as anything that is in the null space of the matrix that we have seen in. This is why we are doing linear algebra with so much detail. Right? When number of equations is less than equal to number of much lesser than number of unknowns, you have infinite solutions, right? You will have infinite solutions, and you will not, and most of them will be something like this, will be overfitting your data, right?
Yes.
So here W1001 to W 1, all are set to 0. And I can just learn W1 to W1000. So that will create all this overfitting exactly like this as we saw in this case, right? We will have variations in the other features as well, but we are not going to capture any of those. Okay. So in these cases, we'll have to reduce the dimensionality of the data somehow. So as dimensionality increases of the data, there's curse of dimensionality. You can see, you can think about this like this. If you have, say, 4 or 10 points here on 2D, on 3D, they will be farther separated out, right? The distances will generally increase in 3D. As the number of dimensions will increase, if the number of data points are remain the same, you will be only having scattered very, very wide data points. Yes or no? I hope you understand.
Yes.
This is called the curse of dimensionality. So dimension increases, data points scattered exponentially. So my question to you is, can I reduce the dimension of the data in such a way so that I retain all the information? So I'll give you one example first, and then we'll come to the. So this is one example. So you see on the left, these are handwritten digit pictures, but they have around 728. They are 28 by 28 images. So they have 784 features, right? This you will be using extensively in your assignment. This is the MNIST dataset. So you have 784 features. But you see what happens in reality is only 25. If you take even 4 or 5 features, na, you will get the outline of this numbers very well. 25 features. Using 25 features only, I can reconstruct the images so well. So I will show you how we reconstruct. But the idea is, even if you have 25 features for the MNIST matrix, MNIST dataset, you can have all the information of the MNIST. Do you agree? Instead of using all the features.
Okay, means 28 cross 28 you made into 5 cross 5.
Yes, I somehow did it. We'll do magically. We'll see how I did it. Even 2, 3, you will be seeing how what happens. We'll see. But somehow I made it somehow to 5 cross 5. I didn't make it to 5 cross 5 by subsampling or averaging. I did it very intelligently. I'll tell you how. But the entire information is sort of remained. Little bit blur can be there, but other than that, everything is retained. It's enough for you to predict. So there is a very, very famous theorem or a hypothesis which says that which is called the manifold hypothesis, which says that all data sets in very high dimension. I'm just saying dimensions, it's actually in manifolds, but that is very advanced idea, so I'll not go. High dimensions actually reside in a much low dimensional space. So even think about a face, pictures of faces, 256 cross 256 cross 3. This is the RGB channel of an image. So this is a image of your face of humans, okay? Face. Each of these pixels can take values from 1 to 125, 1 to 255. So can you tell me how many distinct images can be formed in reality? Like if you take all random possible images, how many images can you form out of this? Zero to 255, sorry. Hello, can you hear me? So you know now what is the image? The image is a
I couldn't get your question.
My question is, say you have an image. Image is nothing but a matrix, right? Image is nothing but a matrix. It's a collection of matrix pixel values. So each pixel value will form a matrix. This is nothing but a matrix. Say this is a face. So my question to you is, say this is a 256 cross 256 matrix, okay? This is an image. And 3 channels. You know that there are 3 channels in an image, R, G, and B, 3 colors.
Yes.
Primary color, so 3 channels. So, and each of these pixel can take value between 0 and 255. This is the intensity of the pixel. How dark or light it is. 0 is dark, 1 is 255 is fully light. So tell me how many different values can this, how many different images can you form? You can form, so one pixel takes 256 values. So how many pixels? So you have 256 cross 256 cross 256 or cross 3 pixel. How many values? How many distinct images will it form? So for every one, you have 256 options.
Acha, it will go in power.
Yes. So to fill up this entire space, you need so many images. So rather 256 to the power this. Sorry, right? So you see there are so many images that is possible. But faces are very, very small subsets of these images, right? You can think of it visually. Think of horses, houses, forests, random image, everything are images, and faces would be very small subset of that. Yes or no? So if this is the entire set, faces would only be this much. Yes or no?
Yes.
Just by thought experiment, you can understand that that's a thought experiment idea, and that is not even a thought experiment. It's a clear cut idea, because you have so many different type of images that you can make. Faces is a very small class of the all classes of images that you can make, and therefore you should actually not require so many dimensions to actually, or so many images. So it may be only say 10 to the power minus some probability of having a face in these images can be as small as finding a needle in a room of hash. So that's the idea. So the idea is, so if the faces are so fixed, they have a particular feature about them, they must be residing in some low dimensional space, otherwise they would have filled the entire space, right? Or due to any other domain, you would have, if they were able to span all data, then they would have spanned the entire data set. Yes or no? The entire space of 256.
Like we have features like nose, eyes, and that.
Yes,
That are constant.
they are constant features. You have very little changes. I'm saying in this pixelated 256 image, you can represent any pixel, any noise also you can represent. Like a screen when TV previous times when we were small, where young people, well, children, we used to see that when the cable connection used to go, there used to be this constant jitter that used to happen, right? That is also an image.
Yes.
So just think of the variety you can get, and therefore it's just going to be very small. So the idea is, although the data is residing in this huge 256 cross 3-dimensional space, this must reside in very say 10 or 15 some dimensional space. I'm just giving an example, maybe 100 at the end of the day, but it can be reduced to much lower dimension. That's the idea. So how can I reduce it? Is the question. Is the motivation clear?
Yes.
So we saw using linear algebra also, and also using thought experiments and manifold hypothesis, that data always resides in low dimensional space, and which is most of the times useless to work with very high dimensional spaces. And people use different algorithms like autoencoders, VAEs, GANs to reduce your data set, but we will be using the simplest classical machine learning algorithm, that's the PCA. So look at this data set that I've given you. Do you agree that most of the information is retained along this axis? right? There's other axes that you have. If you divide it into two axes, we'll see what PC means. Most of this information, PC1 would be enough for me to categorize, because PC2 there is very, very little change, right?
Yes.
So my idea is, let us start with one dimension. So my idea is, let us start with one dimension. I will give you two ways to look at this problem. You can think about it in any way you want. Right? First, minimizing reconstruction loss. Okay. So my idea question to you is, look at this figure on the left, or I'll draw it again. You can refer to that as notes. Right? So this is a vector that you have. This is your data, right? And say this is the dimension or the axis of dimension reduction. Okay. So this is the axis you want to reduce the dimension to. Following so far? So my question to you is, what is the component of this data? So I know the component of this data along x and y Cartesian axis, right? X comma y. But I do not know the component of this data along this axis. If I make this my new basis vector, right? I make these two as my new set of basis vectors. Then I do not know the
x comma y was the data point.
No, this is the coordinates. So let me write x1, x2, and xn. Okay. I'm just showing you x comma y. X is a vector. When I'm writing capital X, it is r to the power d dimensional vector. Y is a scalar, for example. So it can be a vector also, like in multilinear regression, r to the power k. Okay.
All right.
But this is just the data point for the time being. There is no label for the time being. No label. Okay. We are not considering label. See the picture. We'll also consider label. Good question. Okay, but for the time being, this is unsupervised, totally unsupervised. Or to say it is self-supervised, because the data is being used to train itself, right? It's also called self-supervised. Okay. So I will only use this RD and I will try to convert it into some. So RK, K is less than D, much less than D. Okay, this is the idea. I'm saying, say I'm taking the first component only, first component, or the first axis, or the most important axis. Okay, now say I have given you that axis, U is the axis. Tell me what would be the component of the data AX on that axis. This is why we have done linear algebra so nicely. And statistics also will see why it is essential. What is the component of X on U?
X transpose U.
Good. So Z1 would be, or U transpose X. Zi. Okay, for each data point, I'll get this. Do you agree? We are considering only one data point for the time being.
Acha. Here X is capital X, so.
Yes, it's X. X for the time being is r to the power d dimensional space. Okay. When I'm writing this bracket, small bracket, then you think they're coordinates. Generally, I'm not writing coordinates in this course anytime, right? We have used all the coordinates. We have come to the idea of vectors in linear algebra class, and now we are writing everything in terms of vectors, compressing all the equations, right?
Okay.
So this is the U transpose X. So the Zi is the component. But it is a single component of that vector. So now if I ask you, what is this vector? What will you say? Vector, you know that magnitude. What is the vector? Let me
like
write.
the norm of x, I think, divided by.
Good. So you will just do zi into u cap. This is your zi. Do you agree?
Yes.
Good. So now my idea is, so whatever is this u that is actually being used to take the projection, what property should it have? It should have this property, right? Just tell me by intuition. It should have this property, u transpose xi, which is the magnitude of the z, into u. Yes or no? This should have this property that this argmin over u is your u star, such that the norm is 1. Right? It should have this property, that is maximum reconstruction should be obtained. Are you following? So this is the reconstructed data, right? Let me write this over here, vi. So let us, this zi is nothing but u transpose x into u. Yes or no? Okay. It is simply
Yes.
a u vector into u vector. This is the magnitude and this is the direction.
Yes, understood.
This is the vector component of x on vector component of x on u. This is what we have done extensively in our projections, right? We have done this in our classes in linear algebra.
Yes. The original
So now,
minus projected equals is minimum.
yes, so this is the error, right? We have talked about this error also very extensively, right? So this error must be minimum, right?
Yes.
So let me write. So this error for all data points must be for all I. So if I can write the average, say there be n data points, argmin of u star subject to u is a unitary matrix or unit vector. Clear? So I wrote the optimization problem to you. Now, what does this actually mean? So to solve, instead of taking u, I will be just coordinate shifting x. Instead of taking x, I'll just coordinate shift x for the time being. I will show you why. It will give you a better interpretation. So my objective function, the objective of PCA, which is maximum reconstruction or minimum error. Can you tell me what will it be? Summation of I equal to 1 to n xi minus, I'm writing xi tilde for the time being. We'll see why. Xi minus u transpose xi tilde into u. Yes or no? Project the data onto the u space, and then I hope it is clear. I have already told this 5 times now. If not clear, you can still ask. Okay.
Yes.
Xi tilde is, say I am writing xi minus mu, where mu is the mean of the data. I can do that. It's just shifting by a constant. It's just origin scaling. Do you agree? Doesn't change the data anyway. Like the transform, it does not transform the data such that the relationship between coordinates will not change if you transform the origin, right? We have seen that in coordinate geometry in school. The vectors don't change when you change the coordinate axis of the coordinate, right?
Yes.
Okay. So now I'm just writing this as xi tilde. So let us simply write this as. So let us derive the cost now. So can I write this as xi tilde minus u transpose xi tilde u whole transpose xi tilde minus u transpose xi tilde u? Can I write this?
Yes.
Just writing v square as v transpose v, which is dot product with itself is the norm. Good. So now I will have xi. So xi transpose xi. Can you help me with the rest of the terms? Xi transpose xi minus u transpose xi, because the scalar does not change with transpose xi. Okay. Then so I'll just write xi on the left so that there's no issue. Then
Like the first part should be xi tilde transpose xi.
everything is tilde.
Achha,
If I miss the tilde, you don't think it's just my writing issue.
achha, then
We are using
xi tilde xi transpose tilde into mu transpose xi tilde into mu.
this,
Uh,
and
and
the
the
last
last
term is u transpose xi tilde u transpose u transpose xi tilde, right? Scalars I can write anywhere. This is what I'm doing. Okay.
achha, yes.
These are scalars. So these are single numbers. So I don't mind changing them. So A transpose B, I can swap around. That's the idea. Okay. Good. So now you tell me this is a constant. Does it depend on you?
No.
So I can just drop this. We have seen this in calculus, which constants are not required in optimization problems. Now this term, this u transpose u is 1, yes or no?
Achha, norm of u, yes.
Unit vector. Good. Now this term, can I write this as xi tilde transpose u transpose? I just, since it's a scalar, A transpose B is equal to B transpose A, right? A dot B and B dot A are commutable. Okay, so I just change the order. I change the order and I reorder this. I do this terms first. I associate these first, since all matrix operations are associative, right? Similarly, the second term will also be the same. And similarly, the third term will also be the same. So you will get, so all these terms are the same. This is plus, sorry. And so you will get minus u transpose xi tilde xi, right? Any questions? I can derive it each term individually if you want. So I'll do one term clearly and then you will understand. Okay, this I am writing as, because I'll be doing this trick throughout today. So please bear with me. Yes or no? This is okay?
Yes. Okay, then
Now, then I
associate
group
with
this. Yes, I just do associativity. Maths is associative. Algebra is very, very useful. And all these terms are the same. Do you agree? All the three terms. This is this two negative and one positive. So you get
Yes, yes.
U transpose I equal to 1 to n xi minus mu transpose, right? Arg max of u. So this was arg min, arg max of u, right? U is equal to norm of u equal to 1. I'll solve this for you as well, but don't worry for the time being. We'll see after how. But can you tell me what does this internal term mean? This summation also will go inside because u is a constant, right? U does not depend on I.
Yes.
So what is this? This
Like
inner term? No,
projection
I
of
think you.
each individual vectors.
What is covariance of xy? Expected value of x minus x bar, y minus y bar. Yes or no?
Okay, yes, yes.
So this is, so if you have to find between, we have seen if we have to find covariance between vectors, random vectors, covariance matrix, which is referred to as sigma, what did we see? X1, x2, dot 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 xn, y1, y2, yn. This was nothing but expected value of x minus x bar. These are vectors, y minus y bar transpose, where individual exactly the same thing. Each of the ijth coordinate will be x minus xi, right?
Yes, yes.
The ijth coordinate is expected value of x minus xi bar, yi minus yi bar. Yes or no? In a vector form, this is the same. So if we do not have the expected value in reality, we have the samples. We have discussed this many times. So this is the sample expectation, right? Sample covariance. This turns out to be argmax of u transpose su. Okay. This is the optimization problem you need to solve. Is this clear?
Yes.
There is another view of this problem. Very nice view. You can directly tell me from this figure only what should be the view of this? Once you project the data, what should you maximize of the projected data? I saw that reconstruction error is working. What should you maximize for the projected data? Is my second question.
Number of points.
Yeah, you're close. Tell me. Maximizing variance.
More number of points along that axis.
Exactly. Maximizing variance of the principal axis. This is called the principal component because this is the component of maximum variation. Good. So I'll just copy that figure once again. This is the most interesting today's class, and day after tomorrow, like the next class, are the most interesting classes. Like I find it. This is so nice. You are using both your probability and linear algebra just to do machine learning. So nice. So now you tell me the variance of the projected data, variance of Z, what will it be? So Z I write as Zi, I write as U transpose X. It is not a vector anymore. Just bear with me for the change for the overloaded notation. This is not a vector. This is a scalar value. So what will be the variance? Expected value of X minus right?
Yes.
So this is 1 by n xi minus, not x, I'm writing x instead of z, sorry, zi. So this has to be sample again, approximated by samples. It's called Monte Carlo estimate. That is estimating expectation by samples. Can you tell me what is the law that allows us to use sample mean instead of actual mean?
Law of large
Numbers.
Yes.
Good. Law of large numbers. We have shown that also full. Okay, this is okay. All right. Expected value of squared. Now, what does this mean? Do you agree this means 1 by n and you are trying to argmax this? Argmax over mu will give you this. 1 over n zi. Zi is u transpose xi. Yes. And the second term is 1 by n u transpose summation of I equal to 1 to n xi. Correct? I just wrote u transpose outside.
Yes.
Now again, I can do a similar trick. I can write this as the mean of xi. Correct? Whatever we were writing this as mu I or whatever. Did we write this as mu I? Sorry. Yes, we wrote this as mu because it's over all the data, so it's a mu vector.
Like Dada, have you here considered u means? Do you know
I have
u?
not considered anything yet. I considered origin shifting because it will give me the similar form as this one.
Acha, like you are using here in method 2.
Oh,
So,
okay. U I am considering. U is I'm saying the U must maximize your variance of the projected data. The projected data is Zi, right?
acha, means u value we don't know yet. We have taken it as some vector.
Yes, some parameter. Some parameter.
Okay, okay.
But Zi is a scalar, right? That's why we took the variance of Z.
Acha, yes, yes.
Now, U transpose I take outside. Similarly, again, this is if I write U transpose xi minus mu whole square of this. Correct? I equal to 1 to n, 1 by n. No doubts? Okay. So now I can write this as, do you agree? U transpose xi minus mu transpose U. Right? Where I wrote 2 times scalar. So this becomes an associative property. So this becomes U transpose 1 by n I equal to 1 to n xi minus mu transpose U. This is also equal to U transpose SU. Do you agree? Any questions?
Okay, yes, understood.
So this also gives me argmax of U transpose SU. So I'll just write this small here. The objective function is U transpose SU is covariance matrix. Arg max over U. Now see, we have used linear algebra and probability. Now we'll use calculus. Multivariate calculus.
One thing to ask, in
Yeah.
third last step where you have written in the form of square. In the next step to it, yes, there. After that step, what you have
Oh,
done is u transpose xi minus mu whole square.
well,
So you have written in that means that norm form, means multiplying that you will get the square.
no. This is a scalar, right? This is a scalar value. This is just a number.
Yes. Okay,
So
understood. Yes.
I wrote it
Fine.
two times. A square equal to A into A.
Understood.
Yeah. There's a delay, I think, in the. But with that idea, I think PCA is done. It will take only 5 more minutes to complete the PCA idea. Okay, why is it hanging? Yeah. So now tell me, now we'll use Lagrangian to optimize it. Yes or no? We're going to use everything here. Tell me, how will I optimize this? What is my optimization problem? LU equal to. Tell me.
Or like f minus lambda gx, that form you have to write.
There's a constraint, right? The constraint has to be satisfied. Plus lambda 1 minus. I can write this. Square I am taking for my benefit. This 1 means also square is also 1, right?
Acha, yes.
So now dl du, what will this be? This is 2su. S is a symmetric matrix. Why is it a symmetric matrix? Tell me. S is equal to I equal to 1 to n, 1 by n, xi minus mu transpose, right? Okay, it's a symmetric matrix. Take transpose of this.
Okay, yes.
Also, if n is greater than d, generally this will be a full rank matrix as well. Why? Why will it be full rank matrix? I'll tell you. Let us derive this form thing and we'll tell you. So we'll do this. This is symmetric. Where did we see this form? Can you remember? We showed this form was positive definite, positive semi-definite. The G matrix we wrote in SVM, right? We showed V transpose SV for all V is greater than or equal to 0, right? If you multiply any V, you will clearly this is greater than 0, right? Weight is variance.
Yes.
We have just gone in one direction to get this. In the reverse direction, we'll give you the greater than 0 sign. But we'll see if when it will be full rank. But for the time being, bear with me. So since it is symmetric matrix, 2su normal derivative, we have shown this derivative form by using a symmetric matrix, right? dl du plus 2 into lambda u. So what do you get? Su equal to lambda u, right? You remember na u square ka derivative, what is it? This is partial derivative of u square with respect to u1 dot partial derivative of u square with respect to un or ud, whatever dimension u is. Yes or no?
Yes.
So this is what? So the numerator is u1 square plus u2 square dot ud square. So you take a derivative, you get 2u1, 2u2 2ud. Similarly, you will take the derivative for the first term. You can try with a, b, a. This is a symmetric matrix, and you will see you will get the same form. So you get this, right? A su equal to lambda u. So put this value in the original equation. So if you put the value of the original equation, what do you get? argmax u transpose lambda u, which is equal to lambda. Yes or no? So you have to argmax the lambda. Do you agree? Somehow? I put SU equal to lambda u in this equation, right? In this original equation. Do you follow?
Acha, yes, yes.
So I just put this. So when will this argmax be maximum? What is this equation? Do you recall? We have spent a lot of time dealing with this equation in linear algebra.
Like that eigenvector equation.
Yes, this is the eigen equation. So when will lambda be maximum for lambda max? Yes or no? The maximum eigenvalue for S is the principal component, right? The maximum eigenvector you should write. So if you write, we know how to solve this, right? We will put determinant of S minus lambda equal to 0 and we will solve it, right? And then you will get how many lambdas? S1, lambda 2, dot, dot, dot. If there are d-dimensional space, d lambdas, correct?
Yes.
You will maybe you write them in this ascending order, descending order, and then you select. The idea is if you are told to reduce the dimensionality to k, you will select only the first k dimension. So in Python, you will do np dot lineal. This is your assignment problem. Linealg dot eig. You don't need to implement eigenvalue decomposition. It's simple though, but you don't need to. And then S, this will give you eig, evals, and evex. Right? Then you will sort evals and use those sorting index to get the top evex, right? That's all you need to do to PCA, correct?
Yes.
So this is your homework. It will be in your part of your assignment 4. We implement this on MNIST onto two-dimensional space and see on two-dimensional space are 1s and 2s separated out. This will be your homework, and also do k-means on that. Very nice assignment. Try to do it. I have done the solutions myself, so I know it's very interesting. I only set the questions, I only solved. You also try. So now, first k equations you can. So you get, right? So first k of the eigenvalues you will be selecting. First k eigenvectors. So I started with one eigenvector and I got k of them because this eigenvector equation told me that the eigenvectors are the optimal solution, right? To this problem. Correct? Do you agree?
Yes.
So I have been able to solve this equation. Now I will have to write down. Explain maximum variance I have written. Now I will try to write down the dimensionality reduction. So let us at the please see at the end. So now if you recall, okay, if you recall, this was your vector. I have found u1 dot 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 uk. Say k vectors I want to find. K is less than d. Much less than d. For example, d in medical data can be some 100,000 MRI images, MRI pixels. K you may just reduce to 500. Something like that, okay? So now I know the component also, right? This is my Z1 component. Once I project it, I will know the component. Yes or no?
Yes.
So if I ask you what is the reconstructed image, so if I have to reconstruct the data, x tilde, what will be the reconstructed image? So I will have Zi, Z1, Z2 for when I do this thing, right? U transpose X, right? And U is U1, U2 dot 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 UK. KUs I will be taking, right? The top KUs. And X is a single number for the time being, right? single vector. Okay, so I will get what? U1 transpose X, U2 transpose X, dot dot dot, UK transpose X.
Yes.
So I'll get a K cross 1 matrix. This is K cross D, this is D cross 1, and I'll get K cross 1. I'll get it. I have reduced the dimension, yes or no? From D dimensional to K dimensional, I have reduced it.
Acha, yes, yes, yes.
So let me write the D much bigger so that you understand. So intuitively speaking, what should be the reconstruction that you will get? Do you agree this is going to be Z1, U1, Z2, U2? That's how we started with the reconstruction, yes or no? ZK, UK, all the components.
Like,
So
what were the Zi's? Can you tell once?
Zi is the UI transpose X. Now I, for example,
Acha, along U1, along
for this
U2.
time is
Yes.
since X is, so I have to define Xij for you. Okay. Okay. J ranges from
Yes.
1 to N. I ranges from 1 to D. Right. So you will have for every date. Not K. Okay. K. Sorry. K. Right.
Yes.
So your Xi would be Xi1 Z, right? This is the idea.
Yes.
So for every component, you will see what is the vector, right? This is your Zi, comma Ui. This is the vector. Similarly, you'll have k such vectors, and that is the reconstruction, right? At the end of the day, there's no doubts. If you have doubt, you can ask me. So for one component, you had this as the reconstruction. So if you have two components of these vectors, you have taken the projection of the original X only, na? So I'll give you a better example. So your data, if you have all the components projected, say you have all the eigenvectors, what can I write this as? If you project it as Zi1 or Zij equal to 1 to D, right? Ui. For example, if I have two components, one vector I take into two components. If it is a two-dimensional vector, right? If it is a two-dimensional vector, 2, 3, you do X, I roof to get the ith dimension, and you plus do Y, J roof, right? To get X back.
Acha, yes.
So if you have 10 n eigenvectors or n basis vectors, so every d-dimensional space will have d-dimensional basis vector, yes or no? Do you agree? The d basis vectors it will have.
Yes.
So now out of those d vectors, I am going to choose only
Dada,
the
can you
first
check one thing? That should be UI or UJ in
uj
XI cap.
uj.
Acha, yes. Okay, then.
That is uj. Sorry. So the idea is you can simply do. Yes, you can simply do what? You can take a vector, and if you may have n basis vectors, we have seen that in Gram-Schmidt also. You can project this on these basis vectors, and they just take the sum of the projections, right? That's the original vector.
Yes.
Sum of, if I can take a vector X, pi hat, I equal to 1 to D if it's a D-dimensional space. That's what I'm doing. But I am saying from K plus 1 all the way to D, this is not useful for me. Correct? Is the entire picture coming to you? This one I will write as 1 to K Z I J U J I equal to 1 to K plus 1, sorry, K plus 1 to D Z I J U J. This term is the error, right? And this is the reconstruction, right? So xi, so I'm not writing, it should not be xi tilde. It should be xi. Xi should be xi tilde plus error I. Clear? From K plus 1 to D is your error. From 1 to K is your. So for example, if you just have one coordinate, this is your error, this is your xi tilde, right?
Yes.
Good. So now if that is clear to you, can I write xi tilde as, what can I write it as? U1, U2, dot 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 UK and Z1, 1, Z. This is J, right? Z, 1, 2, dot 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 Z, 1K, right? I was writing the first coordinate in the beginning, I think. Yeah, I'll keep the notation, but it's easier to write the other way around. I'll just show you why. This is okay. This is going to give you the x1.
Yes.
This is D-dimensional. Ui is at D-dimensional. This is D cross K. This is K cross 1. So Ui, U x11, x12, dot 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 x1D. Okay. So the reconstruction matrix simply becomes this. What does it become? It becomes this thing. So U is the first K eigenvectors. Okay, I1, U2, UK. Okay, this is a D cross K dimensional vector, right? This is the matrix, the vector form, vectorized notation. Okay, now I will write X as X1, X2, dot 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 Xn, where Xi are R to the power D dimensional space. Okay, clear? These are all training examples. This is D cross N dimensional features. N training examples, instead of writing it in rows, I'm writing it in columns. Okay. Just like we did it in neural networks. It's easier to write this way. Like you can write the other way, but transposes will be changed.
Okay. Okay.
In MLP, we wrote this way, so I'm just sticking to that. So do you agree? So U and Z I can write again. Z1, Z2, dot 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 Zn, where Zi's are how much? Right? K dimensional. Just look at this. I'm just taking these components. K dimensional, yes or no?
Achha, yes, yes.
So now what do I get? I get X is equal to U Z. Let me write it in the elongated form, you will understand. This is the, this is called the transformation. Or this is the inverse transform. Right? Once I know the projections, I'm projecting it back to X, right? X tilde. This is the reconstruction. Do you agree? This is
Yes,
X
yes,
tilde.
yes.
Okay. So U1, U2 dot 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 UK, Z1, Z2 dot 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 Zn. This is equal to X1, X2 dot 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 Xn. This is n D cross N. This is your D cross K. This is your what am I writing? K cross. Right only, na? D cross K. This is your K cross N. So see, K is much less than D. Yes or no? So the forward transformation is simply if you take U transpose of the X, that is going to give you Z. Right? U transpose U is I, yes or no? U1 transpose, U2 transpose, dot 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 UK transpose, U1, U2 dot 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 UK. What is this? This times this is 1. This times this is 0. And all are 0. Correct? This is be a identity matrix K cross K. So why did I write this, you may ask? So I wrote this to show this idea. So X tilde was UZ. So I just multiply U tilde on both sides. Okay. So U tilde X tilde is equal to Z. Clear? So normally what you do is you take U tilde X as the original data to transform it into Z. Right? Because if you take all the parameters, you can just take the first K when you're doing the inverse transform, right? Is it clear? So the forward transform is Z
Hey,
is
Dada,
equal to
what is means which one we want to get? X tilde, that is the reconstruction, or Z?
no Z. But X tilde will help you to understand how is the reconstruction. We need to get that as well. That will tell you how many Z's do you need to get a proper reconstruction, right? How many dimensions do you need?
Okay.
This is just multiplying transpose on both sides, right?
No, mathematically I've understood.
Yes, I'll show you now. Physically also, I'll show you. Now, where is it useful? Now, here is the algorithm. Here is it. So I told you 25 features. I did exactly this. I did PCA to convert it into first 25 dimensions, right? And then I took the inverse transform of the first 25 dimension onto the original space. And this is the reconstruction I get. Clear?
All right.
So, but how do you select the number of features? You select it by the percentage of variance explained, right? You will see the total variance in the data. You will calculate, and then you will see how much variance. So we are calculating the variance like this, yes or no? Right? So every component will give me a variance.
Yes.
You will have a total variance. Total variance will be equal to variance of component 1, variance of component 2, right, or variance of component D. So you will see the percentage variance explained. So here you see 60% of variance on MNIST is just represented by 16 features, right? Just 16 features out of 785 explains 60% of the variance, right? Isn't it so mind-boggling? These 70% of the features explained by, I just kept 70% of the variance and I got this reconstruction. 42 features makes explain 80% of the variance. Just 86 features, one 12th of the feature explain 90% of the variance.
So what does the rest features do? Means
Just have noise. Those components are not at all essential. Just I told you so little bit noise will also be there, right? Just by writing somewhere you can have some extra dots. That is a noise. So for example, y equal to mx plus c. Rest features are not. So here all the features are being compressed. You are not leaving out any features, right? So all the features have information, but they together, just like this figure that I showed you, are actually in another basis space, where another set of basis vectors could exactly give you the same reconstruction or same amount of information as the original Cartesian dimension. That's the idea. Just here, this PC1 dimension is enough, right? The
yes,
rest is just noise. But that doesn't mean that here x1 and x2 does not have information. These are two different basis spaces. You cannot directly compare them. But you can say that the data resides in a lower dimensional space. That you can say, right?
the more amount of data
Hello?
resides in.
I can't hear you.
Hello.
Can you hear me?
Yes.
So I have done the reconstruction also, the transformation. In reality, you do 80%, 90%, or 95% of the variance, depending on the application. That is also done. Good. So with that, we end PCA. Now we are coming to what if
One thing to ask, how
Yeah.
did you calculate that variance?
variance is
Means
just a projection value, na? Variance of Z is expected value of Z minus this. So every you project, so a Zi is equal to Ui transpose X. So Zi for I equal to 1, 2, dot, 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 D, all the dimensions will have some variance, right?
yes.
That is therefore the variance is V1, total variance is sum of the variances.
Okay. Okay.
In reality, when the algorithm does it, it has to find out all the eigenvectors. So it actually knows the components along each of the dimension and knows how much variance it explains. Okay.
Yes.
Good. So now the last thing in your syllabus is the linear discriminant analysis, or Fisher in 100 years back came up with this Fisher's discriminant analysis. So all this while, do you agree there was no information about the labels, right? Labels were not important to us in this. Correct?
Yes.
So if labels were not important to us, how do you make them important? For example, say there are two classes, this blue class and this red class. The PCA direction is this green line, right? In your exam, they will mainly talk about geometric interpretation. You just have to just see the line, right? This is your PCA direction. Maximum variance. Do you agree?
Yes.
Now, if I project the data, the blue and the red are being merged to one another. Yes or no?
Oh, yes. Yes.
So now if I train a model on this y equal to mx to separate this decision boundary sigma y equal to mx logistic regression, you will do badly or not?
Yes.
On reduced features. So the idea of LDA comes from this idea that PCA does not, but it works most of the times, does not practically. We have seen that. I see that every day in my research. PCA does not always give the best direction for, this is more of a contrived example. In reality, we don't have so much contrived example, the opposite. But yeah, best direction for classification. When class labels are known. So normally what people do, take the data, do PCA, get Z and train the logistic regression model or whatever model, supervised learning model on Z, right? So A, Y you do not use here, don't use Y, but use Z comma Y pairs to train the model. Clear? Because it is reduced dimension. But here in this case, we can see that this is not going to help. Do you agree? Instead, if we had this as our basis vector, then clearly we see that the LDA direction, this is called the LDA direction, the linear discriminant analysis direction, will give you maximum separability, yes or no? You can literally, so people do, when they do LDA, directly use LDA for classification. Simply you will be separating this into two places or not? Right? If they are linearly separable, you will be separating them, yes or no? Hello?
Yes.
No, I'm just, I don't know, like I was not audible. Was I not audible? Can you hear me? Okay.
Yes. Can you repeat once?
No, okay. So my idea, I'm saying that, did you understand that when people do X, from X, they do PCA to get the Z, the reduced dimensionality, use the pair of Z comma Y, do supervised learning to train the model on it. Then you can have bad classifiers sometimes like this, right?
Yes.
Like the
Yes.
one. But then if you use some, if I in turn tell you this is the LDA direction, I like this direction better, then it separates the data automatically.
But the data may not be maximally, means the variance may not be maximal in that direction.
Exactly. It may not be maximal, but it will solve the purpose of my separating the data. Do you agree? Variance may not be
That
maximal.
it will solve.
Yes. So I will try to do both the objective somehow. I will try to minimize the variance. We'll see how we'll do that, maximize the variance some way, but we'll also try to separate the classes somehow. So once you do LDA, you don't even sometimes need a classifier. People in neuroscience sometimes use LDA directly as a classifier. Because you see directly you get linearly separable data points. So you take recordings from some monkey doing a task and then maybe use that recording on an LDA space, do LDA and divide it into two different, say the monkey is going to the left versus right. So you take the recording from the monkey's visual cortex or monkey's motor cortex, if the monkey is doing hand movements or something, and then you try to predict just by seeing the neurons spiking in the brain, what is the which side you're going. Just LDA sometimes help. But how do you do this? The idea is very simple. The idea is, again, we are talking about a projection, right? Say, let's talk about the first projection. Okay. So the first projection is, again, U transpose X. Do you agree? This is your, this is X, this Zi is the projection for ith data point. Clear? Okay. If you could, okay. Now, my idea is to, what do I have to do? I want to maximize the means of these classes, right? I want to separate the distance means of these two classes. Yes or no? Here, see, the means were very, very close to one another. Right? Agreed? If I can
Yes.
separate the means in some way, I'll be good. Also, what we want to do is I want to minimize the variance. Minimize the variance. Variance in a class. So if I do both of that, do you agree I will have clusters like this of 2 points where you will have minimized the in-class variance but maximize the separation between the data, right?
Acha. Means this you are doing in D dimensions or K dimensions?
This is in D dimension for the time being. K, I am going to reduce it into 1 dimension for in the next moment. We'll see how.
Acha, acha, okay, okay.
This U vector that I am going to do, this is the U vector, right? After projecting, this is what I got. This is the projection. This is on the 1-dimensional space. I am taking the D-dimensional space and projecting it onto this space, right? On
Yes,
this
yes,
line. So I'm trying to minimize the variance on that line. So it's on the reduced space, K dimension. You're right. On the K dimensional space, I want the variance of the in the class to be low, whereas the separability between class to be high, right? So 2 points I want is desired. Here I have class 1 in the low dimensional space. Not only do I want a low dimensional space, but I also want it to be well separated for the 2 classes, right? Suited for the purpose of classifying the 2 classes, right? Are you following?
Please repeat what you said last.
So from D dimension, I want to reduce to K dimension, right? This is, let's say, the K dimensional space. Originally, this is the D dimensional space. The green line is the D dimensional space, the greens. But say I will divide this into this space. This is the K dimensional space. Yes or no? I'm just like PCA, I'm drawing it. This is my PCA component.
Yes, okay.
So when I reduce the dimension, I not only want, so I want the desires are reduction in dimensionality, right? Dimensionality. Also maintain class information, right? I want to also maintain the class information and not lose it like I lost it in PCA. Right.
Yes.
So how can I not lose the class information? I have to do 2 things. 1 and 2. Separate the means of the classes. You can take other complicated statistics, but it's the simplest statistic. Separate the means of the classes as much as possible. Right? If I can separate the means of the classes, I will be a bit happy compared to if the means were very close to one another.
Yes.
Also reduce the in-class variance. This too, if you understand, then math is like 2 lines. You try to reduce the in-class variance. So you see the data, the in-class variance that you want to make this cluster shrink more and more. That's the idea, as much as possible, right? Then you will be actually increasing the means also, separation between the means also, right? Do you agree?
Yes.
So how can we do that? So let us define a few things. I have defined them here. So the positive class, say the mean of the positive class is mu plus. So please bear with me. I'll just not write mu. Let me write m plus and m minus. Okay. So let the means of the positive and the negative classes be m plus m minus, right? So these are the projections U transpose X for the positive class. So if you're not following, I'll write it separately. So every data point, again, projecting is U transpose X, right? Do you agree? So the CP is the positive class.
Okay,
Set of
okay. Now, P is number of points there.
mod P is the number of points.
Okay, okay. Yes.
And your N is the negative class. I think I wrote it instead of N, I wrote mine. Yeah, N only I wrote. So this will be your mu plus or M plus. I'm writing the mean of the plus class. Okay. Similarly, this will be mean minus 1 by N. Same way I'm writing as I wrote in PCA. U transpose X. So this becomes what? U transpose X plus mean bar I am putting. This is the mean of the positive class, right? Do you agree? This is the constant I can just take out. Okay. Similarly, this one is mu transpose X minus bar. Okay. Questions?
All right. Yes.
So now the in class variance, what can I write? M sigma plus. Tell me. Sigma square plus whatever variance. This is the variance of the positive class. Yeah, tell me.
Like expectation of X
Expectation of,
minus
or I'll not write expectation. Sample I'm going to write. X belongs to P. Okay.
X
Tell.
minus
X minus
again, so that summation
X or U transpose X.
Acha, projection. Yes.
Projections have to be minimized. Remember, the projections have to be minimized. Minus mu transpose X plus bar, right? Whole square.
Okay. Okay. Yes.
Instead of writing the full mean, I'm just writing this here. So this, look at this. This I'm just putting the,
That reduced to X plus.
yes,
Okay. Yes.
the mean. This thing. Seems. So this again, you see, this turns out to be what? U transpose X minus X plus, right?
Okay, X minus X plus transpose.
Very good. This we have already done in PCS, so you are being able to tell it instantly. Right? Again, then what is this? This is the
Covariance.
covariance of the positive class. Right? Similarly, your variance for the negative class will be U transpose covariance of the negative class separately, right?
Acha, yes.
So now you see your loss, what I told, maximize distance between means, minimize the sum of variances class wise. Can you define a loss function for me that will be able to do that?
Like Lagrangian.
Without a Lagrangian, I just want an optimization objective. Lagrangian will come because of the unitary matrix, unitary unit matrix, unit vector. Sorry.
Yes. Like here will be summation.
Some, or should it be just M plus minus M
yeah.
minus? So let us take squares. Squares are better to optimize, right? I want to maximize M plus and M minus, right? And minimize
Yes.
the sum of variances.
Okay, you
I
can write
divide.
minus.
Or we can divide. It will be easier, you will see. Right? So this I want to reduce, this I want to maximize. So done. So now I can write this very nicely as, so M plus minus M minus, let us write it down. Where is it? Here it is. So M plus minus M minus, where is U transpose? Tell me what it will be? U transpose X plus bar minus U transpose X minus bar. Do you agree?
Yes.
This is nothing but U transpose X plus bar minus X minus bar U X plus bar minus X minus bar transpose U. Again, it is a covariance matrix, but it is a rank 1 matrix here, right? It's one vector. We'll see why. Right? So this is, we will write between class variance. This is defined as the between class variance. Right? So this is U transpose sigma B U. Right? The distance between these two, what is the variance between point-wise positive class and the negative class? Clear? Okay, this is equivalent, right?
Yes.
Now optimize this. So this is equivalent to U transpose sigma B U, U transpose sigma T U. This is between means intra-class. So this is how people sometimes refer to them. This is within class. This is intuitively what you can think about. So you're trying to maximize the between class variance, bring it far away, but between class you want to make it less and less variability, right?
What was the sigma t?
Total.
It's a
Sigma,
plus and minus.
sigma square. Yeah, I forgot to mention, but I thought, yeah. You will get this, right?
Yes, yes, okay.
Now, very nicely, I can again do this. So tell me, what will it be? What is the Lagrangian? DLU of this is U transpose sigma B U transpose sigma TU plus lambda into for this problem. Let us first consider without the Lagrangian even. We'll see why it will be solved without even the Lagrangian. Let us not even consider. Let us say that U we are not considering for the time being. U is not unit. You will make it unit after. So after you solve this, you convert it into this vector. Okay. I can do that, right? This is the step I will do. Here, I don't need to do it. We'll see why. Okay.
Yes.
For the time being, let us forget about the norm being 1. Because anyways, we are not using the norm being 1 anywhere till now. Have we used it anywhere? We have not used it. We have not taken projections back to the previous space and so on. We have not done that, right? So we can leave out the constraint without any loss of generality. Do you agree? If you want a unit vector, you can later on project it back. Is it clear?
Okay. Yes.
Because unit vector constraint like reverse projection, but like reprojection is not used here. Okay, so now just this. So dl du I will take equal to 0. Tell me what is dl du? Numerator will be, again, this is a symmetric matrix, sigma b sigma t. This is of the form A transpose, summation of, right? Both are of the form A transpose, so they are symmetric. All covariance matrices are symmetric and positive semi-definite, right? Because V transpose SU SV is greater than 0 for all V, right? Greater than equal to 0. Do you agree? That's how we have defined them, covariance matrices. From variance they have come, right? Okay, so dl du is, tell me the derivative if you can. This is both are scalar, so I can use u by v rule, right? right? If and only if sigma t is full rank, then this is greater than 0. We'll see. This is positive. It has to be positive definite matrix. Otherwise, you can have sigma t u equal to 0 null space equation, right? This will not be equal to 0 for all u not equal to 0. There is no solution to null space, which means it's a has to be full rank, right? Otherwise, it will go to infinity, right? The anyways your denominator you can make to infinity, your 0, by setting u to the null space vector, right? If you make this to 0, then this will blow up to infinity, right?
Yes.
So you cannot have a null space, so it has to be full rank. This is clear to you, this much?
All right. Yes.
Sigma t, no null space, full rank. So now you see this equation. We just write it down. Okay. What can you write this as? Can you write this as sigma bu is equal to sigma t u, right? Let me keep some space. Sigma bu is equal to u transpose sigma bu by u transpose sigma tu. Can you write this?
Yes.
Am I, if my voice is audible, tell me, because I don't understand if the your audio is breaking. Is it my headphone or your headphone? Otherwise my audio will not come.
And it is clear to me.
Okay.
Am I clear?
Yeah, no, now it is clear. Previously it was like there was no sound, very faint. So this is like the optimal solution, right? This is what you want. The optimal max of this lambda max is what you want. So let us write this as lambda max, right? Let us write this as some lambda max. Replace this. This is the initial objective, right? We'll see why I'm writing this as lambda max, but for the time being, let us write this as lambda max. Sigma t is invertible, full rank. We have said. Otherwise, the definition only it will not work.
All right.
So I can invert it. Sigma t inverse sigma b u is equal to lambda max u. See again, I get if I want to maximize it, find the maximum eigenvalue of yes or no?
Okay. Yes.
So instead of solving the ACU equal to lambda u, this became a generalized eigenvalue problem where you have the same S's divided into two B's. Now I have a question, I think, here for your, if you are following linear algebra, to answer. So derive the generalized eigenvalue equation. Show that it can have only one non-zero eigenvector. Sigma transpose inverse sigma b u is equal to lambda u. You have to show that it can have only one non-zero eigenvector. How will it be? How will you know? How will you show? What will you show? Hello? How can you show this? Leave
We
it.
have
I'll
to
just.
find. We have to find out the eigenvector values there.
No, it's not required. What is sigma trans sigma t? Sigma b inverse u lambda u, right? What is sigma b? This is A transpose, right? Where A is equal to m plus minus m minus. Do you agree?
Okay. Yes.
So what are the eigenvalues of A transpose? What is the rank of A transpose? We have done this. Okay, leave. Tell me. If A transpose into A, what is the value? What is the value of A transpose into A? What is the problem here? A transpose into A. This is A square. Am I disconnected? You got disconnected? Right? So sigma B into A is equal to A transpose into A. So finally, I can write sigma B as, what can I write this as? This is the
Yes.
eigenvector, right? One eigenvector, but this will not be the eigenvector in this equation. It's not that simple, but we will be able to find the other eigenvectors from this. Do you agree for all A, there are n minus 1 or d minus 1 perpendicular vectors? Right? If you have one vector, A belongs to d-dimensional space, what is the how many number of perpendicular vectors to this independent vectors does it exist?
Acha, acha. Yes, yes. D minus one
D
perpendicular.
minus 1 vectors. So now you see there will be d minus 1 vectors in the null space. So say
Okay, then dot product will be 0, right?
good. A null 2. This is very interesting, very important question for your interviews. If you are trying to give, they will ask you this question. All this will become 0. So you have only one eigenvector, right? So you can easily find this because the rank of this is only dependent on only one vector, right? So the rank is 1. It means that only one eigenvalue exists. So therefore, there are all R of this are 0. All other eigenvalues are 0. Only one exists. Right? So this actually acts as a classifier instead of a dimensional reduction, because you would be at the end of the day give a scalar value, right? If that is not useful as a feature in general, right? Because at the end of the day, you're getting only one u. You're not getting k u's, right?
Yes.
So that is why LDA will give you just one vector. So now if you have k classes or c classes, what can you do? We can just write the same equation. I'll just take 2 more minutes. This equation is sigma b. Now for k or c classes, right? Let me draw it here nicely so you'll understand. So 1 class, 2 class, and 3 class. So do you agree you want the decision boundary to be something like this? We have seen this in the iris dataset also. We wrote the code.
Yes, but can we make it a straight line, means one dimensional?
No, that we cannot. We will need multiple hyperplanes like this to divide it into multiple k spaces. We can also divide. We can do that. We can also take one of the vectors, but that will not give you better accuracy. You can always take one vector and tell I will select that vector to categorize. But here you will see I'll get more vectors instead of one. So now you see m plus and m minus this thing for two classes. I'm trying to generalize to C classes, so I'll show you. This is what I was getting as sigma b. Do you agree? Okay.
Yes.
So can I write this as mi m plus plus m minus by 2 m plus plus m minus by 2 transpose into 4, or just proportional to this? Here it is into 4, but in other cases it can be like, is it clear? This is the same as m plus and m minus. Now this is, do you agree, the average of the data? M you said yes and did not say this should be m minus. Okay, just one moment. 2 times m plus. Why am I getting an opposite sign? Okay, it is correct only, I think. This is 1. And the other one I can write as, sorry, very sorry, plus m minus so just remove this. This is not right. Okay, can I write this as? Always see the steps, otherwise, see, I got a mistake. Yes, I can write this. Okay, so what I can do is this m plus and m minus, I can write this as. So you see this step that I get over here. If you take one of these terms. Okay, can you hear me? Any issues?
Yes, I was facing some network problem.
So this is, do you agree this is the same thing? I can write it 2 times.
Okay, yes, as difference.
Yes, so this is also m plus m minus m. So m minus m. So if you write this, you will get m minus m plus by 2 m minus. So what I essentially did is, let me just write the between step so that there is no confusion. I did m plus m minus by 2 m plus m minus by 2 plus m plus or m minus m plus by 2 m minus m plus by 2. Clear? This is what I did. Into 2 into 2. Clear? No problem if I do this.
Yes.
And that this is equal to this and this is equal to this. Do you agree? If you just add and subtract m plus from here or m minus from here, you will get this. Yes or
Yes.
no? Good. So now this is the average mean, right? M, or the mean of the total data, but not taken with directly, but taken after averaging. First average across classes and then average across all the data points, right? Then you can write this as, can you write this as I equal to 1 to C mi minus m, mi minus m transpose as sigma b. For two classes, it is true. For C classes, right? You want to separate the classes as far as each class as far as possible from the mean of all the classes, right? That is what it's turning
Yes.
out. So this, instead of 2, I have written it into C terms. Okay. So now your loss function becomes, what will it become? Tell me. Same thing.
Like
You
not you are using. Okay, understood. Yes.
it will be the same class, same loss function. Again, the solution to this is will be again the same, right? This is sigma total inverse sigma b u is equal to lambda max u, right? Same solution. I'll give you a moment to digest this and then I'll put the concluding statement. There's a statement to have at the end of this. This is clear to you? So for two classes, you had two separations, like two means, and for C classes, you will have C of them, right? It's basically, if you take the intuition, it is trying to say this is the mean of the data, trying to separate all the data as far as possible from the means, from the mean of the data. Clear?
Acha, yes.
But the mathematically it is clear, right? Intuitively it may be clear, but one, if you only intuition is clear, you must also mathematics also must be clear, because I'm putting a lot of effort into that. I hope it is clear. From two classes to C classes. Okay, so now I tell you, in here you have C minus 1 eigenvectors solutions. At most C minus 1 non-zero eigenvalues. Can you tell me why? This will be, you can tell me this from this idea. So let us write this mi minus m into this mi minus m as some capital M. Okay, capital Mi, right? So your sigma b can be written as capital Mi transpose I equal to 1 to n. Okay, I can write this. So now you can
Yes.
treat this as a simple linear regression problem, linear problem. So capital M, remember capital M is R to the power D dimension only. It's not a matrix. So these are all rank 1 matrices, or C of them. C rank 1 matrices. Do you agree?
Yes.
Now, if I tell you sum Mi I equal to 1 to C, what will you get? Capital Mi, if you sum, you will get, if I say root into root that, so you'll get 1 into C Mi minus I equal to 1 to C right? 1 by n summation of j equal to 1 to CMI. Yes or no?
Yes.
Tell me, what is this? What is this?
अच्छा, C into C, 1 by C, summation M1. Oh, 0. Yeah, wow.
Yes. This is 0. So now I know one property that this is 0, right? I know.
Yes.
Not this is 0, sorry. Mi is 0, I know. Sorry. So can I write this as I equal to 1 to C minus 1 Mi is equal to MC? Can I write minus MC from this equation? Correct?
Okay. Yes.
Because summation of Mi was equal to 0.
Acha,
So
yes.
I
Up to
wrote,
C 0 to distribute it.
yes. So now in this original equation, I will be doing something. Some maza I'll do. I'll write this as 1 to C minus 1. I know this. We know. I'll just keep it as we know. So Mi transpose plus I plus MC transpose. Can I write? This is my sigma B. Correct?
Yes.
No, I don't have space. So where do I get it? Okay. Where did it go? Here it is. So I'll just write it somewhere over here. There's space here. Okay. So I know sigma B is equal to I equal to 1 to C minus 1 Mi transpose plus MC into I equal to 1 to C minus, or let me write MC transpose once again. Can I write MC transpose as? What can I write this as? Or what can I write MC as? Either of them, tell me. Minus I equal to 1 to C minus 1 Mi? Yes or no?
Okay, yes.
So what does this become? Summation of I equal to 1 to C minus 1 Mi transpose minus MC summation of I equal to 1 to C minus 1. Let me write MC inside Mi transpose. Yes or no?
Yes.
So this becomes what? I equal to 1 to C minus 1 Mi into, or Mi minus MC Mi transpose. Yes or no? Yes.
Yes.
So how many terms are there now? C minus 1 terms. So if you have C minus 1 terms, so again, recall, this has to have rank of this, rank of sigma B has to be less than equal to C minus 1. Why? Recall, rank of A plus B is less than equal to, we have proved this in linear algebra. Yes or no? Two matrix, sum of the rank is less than equal to sum of individual ranks. So if you have summation of Let me write this entire term as some chi I less than equal to c minus 1, or let me write I equal to 1 to c minus 1 rank of chi I. What are the individual rank of chi I? What rank matrices are there? AB transpose. What is the rank of AB transpose we derived just now?
It was rank 1.
Rank 1. So this will be less than equal to rank c minus 1. Do you agree? This is what I was saying.
Acha, yes, yes.
So it max can have c minus 1 eigenvectors. Normally, now the only remaining bit piece that is left is the question that you did not ask me. Is sigma t has to be, what has to be? Full rank, right? Correct?
Yes.
How is it full rank is the question. So this is sigma t is, let us take full sigma, full data. This will be a proxy for the without loss of generality because we are just adding sigmas. So instead of dealing with the constants, I'm just taking the sigma. So n data points, x minus mu transpose, right? Say x is d-dimensional, where d is less than n. So normally speaking, do you agree that again they are all rank 1 matrices? They would be less than equal to n, right? Correct? The rank of sigma, right? But n is greater than d, so you have to take the minimum of n comma d, which is less than d. Right? D-dimensional. It has to be, we want it to be d-dimensional, right? D rank must be d of sigma. But how do you show it is equal to d is the question. Here is the answer. Think about it. So this, do you agree, can be written as, so I will write this as x i's, x tilde i's. Can you think of this as xi, x1, x2, dot, xn, x1 transpose, x2 transpose, dot, xn transpose. Right? So this is d cross n dimensional, this is n cross d dimensional, right? We'll get n sums, yes or no? This will get this. This is same as this.
Yes.
Now you tell me rank of A transpose, what did we find? Was equal to rank of A. Because this is equal to rank of A transpose minus rank dimension of null space of, again I forgot, null space of A intersection column space of A transpose, right? And we saw that null space of A and column space of A transpose were non-intersecting. So this was 0. So rank of A transpose is rank of A. We saw that. That is equal to rank of A transpose. Correct? Yes or no? Okay, so have a look at it when you're free. But anyways, have a look at it, revise it. But if they have the same rank, then rank of X is equal to number of independent training examples, right? Correct? Number of training examples. They are independent number of training examples. So do we know that each x is some f of some latent dimension plus some noise, right? There is always some noise. And when there is noise, there cannot be dependent vectors if you have more number of vectors, right? Because noise will always take it into other spaces. With no probability can you have dependent vectors just from noise, right? Because those are specific cases out of a infinitum case of, say, normal 0 I. This is clear. So if you have more training examples than the data point, a few more, like approximately 10% or 100, 10 times more or 5 times more as the number of features, then you are guaranteed to have sigma t to be a full rank matrix. Is it clear? Okay, so if you have C classes, at most C eigenvectors you can have from LDA, one class, you have only one output. Is it clear? Any questions, or I'll stop? With that, we stop with all dimensionality reduction. In the last class, next time, we'll be doing the last bit of the course, that is expectation maximization. I really wanted to do it. Once you do that, all the unsupervised learning we have done so far will become, you will have a closure on all the unsupervised learnings that we have tried and learned so far. So with that, if you don't have any questions, I'll stop. Any questions?
No.
Okay, so I'll stop recording.